In order for us to do any analysis of the games we've defined, we need to understand what strategies are. So these are the most important things that we're going to work with. So strategy is a complete contingent plan for a player. So what do we mean by that? So a complete contingent plan. Let's unpack this a little bit. The plan part says what is the action you're going to take, what action to take. Contingent is given that you reached some information set. And the reason we need to make sure to include the word complete here is because we have to be able to say what this player is going to do at every single information set where that player is called to play. Importantly, even if we look at a strategy and it's not possible for given that strategy for the player to be reaching a given information set, we still have to say what he's going to do at that information set. And I'll get into why that is in a little bit. So this is for every, very important, for every information set. So that's what a strategy is. So let's look at an example. In this game, for player one, there's only one information set where this player could be called to play, and that's at the initial node, the initial information set. And so a complete contingent plan for this player simply says, what does player one do at that initial node? Either he plays H or he plays L. And so he has two possible strategies. For player two, there are two different information sets. So a strategy would have to say what he does in each of those different information sets. Typically what we're going to do is to write the strategy that he's going to play as a list. So here, for if he's going to play action H and L prime, I would write H L prime. Or alternatively, for L L prime, I would write L L prime. So if you see the list L L prime as a strategy for player two, you know that in the top information set, he's going to play L, and in this bottom information set, he's going to play L prime. Now you can see why in the definition of an extensive form, we insisted that if there are actions at two different information sets, so you look at this information set and this information set, there were similar actions H and L that player two could take, but given that they're different information sets, we insisted on labeling them the actions differently. So this action H is distinct from this action H prime because they're being taken at different information sets. That's what allows us to write down a list of actions that the player is going to take. And for each action, we know exactly which information set he's making that action at. So if I say player two is going to take action L, well, you know exactly where he's going to do that. Action L is only available to him at this information set. And so that's why we insist on labeling the actions distinctly. So you can only take a given action at one of the information sets. So how many distinct strategies does player two have? Well, there are two distinct actions that he can take at the top information set, and there are two distinct actions he can take at the bottom information set. So in total, there are then four distinct strategies. So what are so HL prime, LL prime are two of the of those strategies. And what are the other ones? Well, he could do H prime, and he could do LH prime. So 1, 2, 3, and 4. So there are four different strategies that this player could choose from. We call this the strategy space, or sometimes a strategy set, for the player 2. So in general, SI is the strategy set for a player, player I. In this particular, so this is in this particular example, S1 is very small. There's only two different strategies, either H or L. S2 consists of these four things: H, L prime, H, H prime, L, L prime, and L, H prime. I want to emphasize here that the strategy has to be a complete contingent plan. So let's emphasize that a strategy is a complete contingent plan. And so this game will help us illustrate exactly why that is and why it has to be that way. So let's take a minute to understand this particular extensive form game. We've got two players, players 1 and player 2. And player 1 is the one who moves at the very first node. So the initial node has player 1 moving, and player 1 can either choose in or out. If player 1 chooses out, then the game ends and they both get payoff of 2. If player 1 chooses in, then it's player 2's turn to move. Again, player 2 has the same choices, either in or out. If player 2 plays out, again the game ends. So if player 2 plays in, then it comes back to player 1. So this is player 1's second information set. And he has two different choices. He can choose to play action A or action B. If he plays action A, they get 4 and 2. If he plays action B, they get 3 and 4. So because player 1 moves in two different information sets, a complete contingent plan would tell us what he does in each of these. So here he could play either O or I, and here he could play either A or B. And that's why we have these four strategies here. OA, OB, so he plays O here, and there's two different things he could do here. Or he could play I here, and there's two different things he could do here. Player 2, on the other hand, only has one information set and two actions at that information set. And so those are the two strategies for player 2. Now, if we just wanted a recipe for how the game is going to proceed from player 1's perspective, anytime he plays O, the game ends. So what do we care about this information set? I want to give you just one more example so that we can be clear about what a complete contingent plan is. Now, the number of information sets might actually be quite large. So in the games we've looked at so far, there are a finite number of information sets. But let's think about a game where there's actually an infinite number of information sets. Think about the following game. There's two firms. So it's an example with two firms. It's so these two firms are the two players, player 1 and player 2. Each can pick a quantity Qi. So firm I picks a quantity Qi between 0 and some upper limit Q bar. So Q bar is some positive number. The demand is given by, the inverse demand is P of Q1 plus Q2. So the price of that they're going to get for their wares will be P of Q1 plus Q2. So the payoffs so this is the demand. So this means that the payoffs are UI. So player I's payoff is going to be QI times P of Q1 plus Q2. We'll assume that they're able to produce their goods at zero marginal cost. Now, player 1 moves first. So the timing of this game, firm 1 moves first. And announces Q1. Firm 2 sees Q1 and announces Q2. So firm 1 is the one to move at the initial node. So what is the strategy space for firm 1? Well, firm 1 strategy space is just they just have to pick Q1 between 0 and Q bar. So firm 1 is going to move first. They're going to pick some Q1, and sometimes what we'll do is we'll write I'll write it this way to indicate that rather than having, so if, for example, we could have looked at an alternative game where they could have picked 0, Q bar over 2, or Q bar, right? So there's only 3 different quantities that they could have chosen. But here, because there's a continuum of quantities that the firm could choose, the extensive form has an infinite number of branches from player 1's initial node. Following each of those, there's going to be a node for player 2 where they pick Q2. Again, Q2 is going to be in 0 to Q bar. So a strategy for player 2 would be having observed Q1, so you look at some Q1, and based on that, you pick Q2. So it's going to be a function from the interval 0 to Q bar to 0 to Q bar, meaning that, remember, each information set for player 2 here is identified by one particular Q1. So S2 of Q1 is the quantity chosen by 2 when he sees Q1 chosen by 1. So the strategy here would be a function from the strategy space of player 1, or the action set of player 1 at this information set, to all the actions available to player 2. In general, you can always think of a strategy as being a function from information sets to actions.